Today we'll go through recording the workshops. This is complimentary part from Society of Mechanical Ventilation Conference. Uh, we understand there were some problems recording of the workshops, so we will do this instead, and hopefully this will be beneficial. Before we start, again, this video will be recorded and we'll send you the links and it will be free. You can watch it at any time. I put some slides as objectives of today's talk. We'll talk about just some of the slides and then we'll go through um, a long simulation. We have two online long simulation from Hamilton ventilators, so we're gonna go through those. Um, we'll have some times to answer any questions or some chatting. We'll monitor those at the end. Um, we'll also toggle between both simulators because not all of them, both of them have the same capabilities, so we might change a little bit. Um, Again, some of those topics are, of course, interlapsing, so we might not talk about the exact same order. Uh, especially like PEEP and esophageal balloon and recruitment maneuvers, but we'll try to cover most of them, if not in order. So again, the objectives is we're going to talk about basic waveforms, respiratory mechanics, PEEP, recruitment maneuvers, esophageal balloon manometry, and transpulmonary pressure, mechanical power, adaptive modes, and asynchronies. And I'm sure you all know those. Those are simple, basic stuff, but we'll just go through them quickly. What is compliance and elastance? Compliance is 1 over elastance, and elastance is 1 over compliance. It basically, this is the whole respiratory system. So if you look here in the yellow, this is the airway pressure, pink is the flow, and green is the volume. This is a pressure controlled mode, and this is a volume controlled mode with constant flow. So in pressure control mode A and B, the peak and the plateau. If your flow is long enough to reach baseline, you don't really need to put an inspiratory pause because the plateau will be equal the peak. So how do we calculate it? Basically, the compliance and pressure control, it will be the exhale tidal volume over the plateau pressure minus the total PEEP. And it's very important to stress it's not only the PEEP you dial on the ventilator, it's the total PEEP in case if the patient has auto PEEP. In volume control, again, those are the classic measurements. If you put inspiratory pause, you're going to get A, which is the peak inspiratory pressure, B is the plateau pressure, and C is the total PEEP. Again, you might need to put an expiratory pause to get the total PEEP as we talk later. And the formula would be tidal volume, exhale tidal volume over plateau pressure minus PEEP. Now, this, what we talked about was of the whole respiratory system, and it's important to recognize that there is, those are just to inflate, the compliance is just a force need to inflate both the lungs and the chest wall. So it's important to basically decompartmentalize them. How are we going to do that? We need an esophageal balloon. So again, A is the airway pressure. We're still in the volume control with the constant flow. B is the esophageal pressure tracing, which is a surrogate for the pleural pressure. Now C, the ventilator already constructs transpulmonary pressure, which is basically the airway pressure minus the esophageal pressure, gives you that transpulmonary pressure. So how are we going to do that? Again, let's do total respiratory compliance, tidal volume, which is here, over the plateau pressure, which is this one, the white line, minus the total PEEP. So in this example, our tidal volume is 500, the plateau pressure is 27, the total PEEP is 15, so you get a compliance of 41.6. How about the chest wall? And sometimes the chest wall is high, even in ARDS, We always think it's only the lung, but definitely not. Chest wall edema, trauma, sepsis can all worsen. Ascites can all worsen the chest wall. How are we going to calculate it? So it's a total tidal volume again, minus the end inspiratory esophageal pressure, that white line here, minus the end expiratory esophageal pressure, the red line here. And you can tell in this example, there's no much really difference between the end inspiratory and the end expiratory. But sometimes if the patient is active or have very high chest wall compliance, low chest wall compliance, there might be marked difference. So in this example is 500, here minus 17, over 17, minus 12, equal 100, which looks like very normal. How about the lung itself, if we're mostly interested in the lung? So now it will be the tidal volume, but we now need to look at the transpulmonary pressure. So the end inspiratory transpulmonary pressure, that white line, minus the end expiratory transpulmonary pressure here. So it's basically tidal volume over this white line, end inspiratory transpulmonary pressure minus end expiratory transpulmonary pressure, or it's called the transpulmonary driving pressure. So this is important if you really want to calculate it. One quick thing I want to talk about is time constant. And time constant is a very actually simple phenomena that happens coming from electric engineering. Time constant is basically compliance times resistance. And that's the time that takes to either fill any object, in our case is the lung, or to exhale empty the lung. So each time constant, there is a decay of 63% of the volumes. So for example, if our flow here is 100, after one time constant, it will be 37%. Then another 63%, after another time constant, it will be almost 12. So usually to totally inflate the lung or deflate the lung, you need about 4 time constants. The normal time constant is about 0.8 to 1 second in normal lungs. Restrictive lung, like in this case, restrictive lung, like in this case, like probably ARDS, you can see that the lung is emptying very, very fast. So very short time constant because the compliance is very low. And if you look at this other example here, it's an obstructive. You can see that the lung is still filling. There's 2 time constants and still exhalation started after the second one. Same here, the patient is exhaling and only 2 time constants and the next breath starts. Because the lung didn't have the time of the 4 time constants to happen, patient developed auto PEEP, which we'll talk about in a little bit. So sometimes it's very important and nice to just, because as soon as you look at the ventilator and you look at the waveforms, it gives you an idea, are you dealing with almost a normal lung or a restrictive pattern or an obstructive pattern. The next slide is auto PEEP. Auto PEEP, of course, we all know it's called intrinsic PEEP. And important to know that the ventilator does not tell us the auto PEEP. The airway pressures, look, whatever you set the PEEP. If you set the PEEP at 5, it will show you 5. But if you look at the expiratory flow, and again, very important, just by looking here, you can see that there's auto PEEP. So if the patient is in shock and you're not sure why, take a look here. The problem might be all auto PEEP, and if you correct it, the patient might improve. So what do we have to do? As we all know, we put an expiratory pause. So here we put expiratory pause during the exhalation, and you can see the airway pressure went up. So the total PEEP is that big orange arrow, and the PEEP that you dialed is that small arrow. So the auto PEEP is the difference between here and here. Again, it has a lot of course, hemodynamic problems, can cause a lot of asynchronies and patient discomfort and agitation. We'll jump into mechanical power quickly. Again, this concept of mechanical power all coming from physics. Mechanical power is basically the work done to get a volume. So it's pressure, the ventilator or the patient put pressure to get a tidal volume. So that's work. if you multiply that work by how many respiratory rate, you get the power to breathe. And we all know most of the studies showed that mechanical power could be related to mortality. So this is the pressure volume curve in a patient, again, on volume controlled mode with a constant flow. And that's what you see in a patient. So we can divide the mechanical power into resistive part, that green area here, which is just the energy takes to get the air through the airways. And we can divide it into elastic part. The elastic part is to get the air into the lungs, past the airway resistance. So we can again subdivide it into tidal elastic part, or called dynamic elastic part, or PEEP elastic, which is the elastic static. If you look here, that's the same patient, but switch to pressure control, and you can tell that the area under the curve here is much bigger, bigger than the area under the curve for the volume control mode. But the same idea: resistive part, the green, elastic part, this left side, and again you can divide it into uh, elastic static, which is the PEEP, and elastic dynamic. And again, there is a lot of talk of which is the more important. Do we have to worry about resistive one? Do we have to worry about PEEP? Maybe the most important is the tidal. Again, we're not 100% sure. So anyway, to calculate the mechanical power, you really have to be an engineer or a mathematician to get that area under the curve. And if it's very smooth like this, you might be able to. It really needs a lot of mathematics. So they came with other formulas as surrogates for the mechanical power. There's so many of them, but I choose for you here two simple ones and been validated. Of course, because as we said, the area under the curve in volume control is different from pressure control, so there's two different formulas. In the volume control here, it's expiratory minute ventilation, minute volume, multiplied by the peak airway pressure, plus the PEEP, plus the inspiratory flow divided by 6, all divided by 20. So let's take a look for example. So in our example here, the minute volume is 5.8, multiplied by the peak 23, plus the PEEP is 5 here. The peak inspiratory flow is 43 divided by 6, all divided by 20. You do the math, you get 10.2 joules per minute. Let's do in pressure control. The formula is a little bit different. So 0.098, which is basically conversion factor, which is similar to the divided by 20 here, multiplied by the respiratory rate and tidal volume, which is again the minute ventilation, minute volume, multiplied by the inspiratory driving pressure, inspiratory driving pressure plus PEEP, which in this case will be the peak inspiratory pressure. So let's take a look at the numbers. 0.098 multiplied by respiratory rate of 12, multiplied by tidal volume, but here in liters. So the 500 will come to 0.5, multiplied by the peak inspiratory pressure, as you can see here, 20. So you come up with 11.71. So it's a little bit complicated or complex, but you have to, again, calculate it every time patient's respiratory rate changes, the tidal volume changes, you make changes on the PEEP or the driving pressure, you might need to keep calculating it. Now, this busy slide about asynchronies, and we're not going to go through all of them. The problem with the online simulators, sometimes hard to create all kinds of asynchronies. We'll try to create some of them. But work shifting, we'll see how the patient effort might affect the waveforms. Sometimes it's called flow starvation, flow asynchronies. Usually you can divide it into cycle asynchronies, either early cycle, meaning that the ventilator stops the breath early, or late cycle, when the patient cycles to exhalation early. Sorry, I'm going back to this slide. So either cycle or trigger asynchronous. Trigger asynchronous usually failed trigger, double trigger, auto trigger. Here's some examples of this. This is called delay triggering. Most of the time you can identify asynchronous by looking at either the flow or the airway pressure. Usually ventilators, new generation ventilators these days, detects very quickly the patient between when he wants to breathe and when it delivers the flow or the pressure. So if you look at, there is a big delay here in the flow. This is called delayed asynchrony. Usually the normal trigger time in new generation ventilators is almost 0.03 or 0.04 or maybe 0.06, depending on what ventilators. So very, very short. But if you look here, there is patients start to breathe here, and it's like, the ventilator start to give the breath here. And we'll try to show it a little bit. Ineffective trigger or missed trigger, and you will see like a little bit of bump on the flow, but there is no breath. Auto trigger, meaning the ventilator keep giving the breath, but it's the patient sometimes might be totally paralyzed. So it could be detecting, heartbeats, water in the circuit, any air leaks. The delayed trigger and ineffective trigger or the missed triggers that we talk about, most of the time it's from auto PEEP, setting very high tidal volume or very high pressure, or the patient's effort is low. Let's go to the other one, double triggering, which I told you about. Most of the time, again, two breaths, because usually the inspiratory time is very short, so the ventilator cycles to exhalation, but the patient is still breathing, so the ventilator will give him another breath. Sometimes it's hard to determine, is it a double trigger versus an auto trigger, unless you have esophageal balloon or diaphragm in NAVA, diaphragmatic activity, electrical diaphragmatic activity. In the cycling, meaning switching from inhalation to exhalation, you can see here this is an early cycle. Hard to tell, but you see the flow is going up, and you see this complex convex here, meaning that the patient inspiratory effort is still going, but then the ventilator cycles to breath, to exhalation. Depend if your inspiratory time is short, or if you're in pressure support, your expiratory sensitivity might be set too high, so the time is short. You can see the difference between now, this is delayed cycling. The patient here was convex breathing and he stopped breathing, and you can tell the difference in the slope here, but the ventilator kept going. So here the inspiratory time is too high, or your expiratory sensitivity is set to be too short, so the inspiratory time is high. So we're trying to match the patient's brain to the ventilator cycle. With this, I am going to stop sharing those slides, and we will go switch now to the online simulator. And we'll talk about the same things again. Okay. I hope you can all see the ventilator screen here. Quickly again, this is a G5 Hamilton, and the nice thing about it, you can use it. Actually, it's free to download for education purposes. You can make the patient here, you can choose normal respiratory system, ARDS, COPD. You can control even the resistance, increase it or decreasing, the compliance, the patient's respiratory rate, and the patient effort. So it's very, very nice for teaching and illustrations. Quickly, we'll do what we talked about. So the waveforms quickly. Yellow is the airway pressure. Pink is the flow. Green is the tidal volume. So we are right now on a pressure controlled mode. And I want you to see, like here, what we control is from the ventilator, respiratory rate, the amount of pressure controlled, the PEEP and the FI2. And let's calculate the respiratory mechanics. So in this case, you can see that the flow is not going down to the baseline. So you need to do an inspiratory pause. In this simulator, you can do an inspiratory pause. So what I will do is I will increase the inspiratory time to make my, yep, to make the flow went to zero. So whatever I'm having here is the plateau pressure. So we're having a tidal volume of about 850. So our respiratory compliance is 850 over 20 minus PEEP of 5. So 800 divided by 15 comes about like, I don't know, 55 or something. But to do the classic one in volume control, so we'll switch to volume control and I will switch to the constant flow. I'm going to put a little pause to give me a plateau pressure. Of course, when you do inspiratory pause to get a plateau pressure, you really need a longer pause. Again, this ventilator wouldn't let me freeze or make a pause, so I just put here to give us a pause. So again, my tidal volume is, let's wait a second, it's set at 500, so the tidal volume will drop to 500. So 500 minus my plateau pressure, for example, here is going to drop to about 12. So 500 divided by 12 minus the PEEP, so equal 500 divided again by 7, you get about 50 or so. Let's talk about, I want to talk about uh, setting the PEEP and setting and transpulmonary pressure. So I'm going to stop sharing here and I will go into my other simulator. Sorry, bear with me here. Okay, so this is another simulator from Hamilton. And what you can do with it here, you can do some pauses. So we'll go with this. We'll change this layout. Again, the same thing. We are pressure, airway pressure flow, but instead of volume, I will put esophageal pressure and I will put transpulmonary pressure. So since we're here, let's talk about the esophageal balloon manometry a little bit and how we're going to use it. Um, so esophageal pressure here, you can see during inspiration it goes up and during exhalation it goes down, but that's in a passive patient, meaning that the patient is paralyzed or have no efforts whatsoever. If the patient is active and doing work, you will find usually before the breath that the esophageal pressure will go down and then the ventilator will trigger. And that helps a lot in asynchronies. But in any case here, so let's calculate again what's our um, uh, chest wall compliance and lung compliance like we talked in the slide. So for chest wall compliance, we will calculate it's the tidal volume. Let's freeze this. Okay, it's the tidal volume for 130 divided by the difference between inspiratory pleural pressure, the highest one, which here is telling me it's about 6, minus the lowest one and exhalation. Oh, I'm sorry. The end inspiratory one is actually 4, and the end expiratory one is about 1.5. So that the chest wall compliance will be the tidal volume for 100 divided by 4 minus 1.5 equal 2.5. Again, sorry, do the math. So it's 400 divided 2.5, about 20. Okay. How about the lung that we're interested more again in it? So it will be the end inspiratory transpulmonary pressure. Again, imagine, and I can set it actually to do an inspiratory pause here. Okay, so let's do an inspiratory pause. Okay, so my end inspiratory transpulmonary pressure, that white line here is 8.4. And we'll have to do an end expiratory transpulmonary pressure, again, to see what's the transpulmonary driving pressure. So the end expiratory transpulmonary pressure here is 3.7. So I think it was 8.7 minus 3.7, that's 5. So the lung compliance would be the tidal volume, again, the 400, divided by the transpulmonary driving pressure, which is 8.3 minus 3.5, I can't remember. So 400 over 5 or something, that would be 80. I hope this was okay. So one of the important things again for esophageal balloon, not to only monitor the mechanics, is to set the PEEP. So I am gonna make that patient here an ARDS patient. Keep him passive. So let's take a look what happened here. Of course, I'm in the same settings. I'm actually in ASV, so I will go to just pressure control right now, and I should have set the alarms so it doesn't bother us. We'll increase the volume, we will decrease the volume. Reduce the pressure, and because it also gives us an estimate of the end tidal CO2 and the oxygenation, so we don't want it bugging us. We'll set it low. Okay, so now we're in pressure control. Again, here we have a patient rate of say 20, pressure control, driving pressure, inspiratory pressure 13 over PEEP of 5. You can notice, of course, when the patient is ARDS, you can see the lung inspiratory flow goes up very high, expiratory flow goes very deep and wants to collapse very closely. So by just looking at this patient, you can tell that he has a restrictive problem. Look at what happened to the pleural pressure. It went high, almost like 14. Now take a look at the inspiratory and the expiratory transpulmonary pressure. Now I'm going to put a pause here. The end inspiratory transpulmonary pressure is 3.9. And that's actually pretty good. Most of the studies showed you want to keep your end inspiratory transpulmonary pressure below 12 or 15 in a healthy lung. So of course, the lower, the better. So 4 is pretty good, but of course, like that, look at the tidal volumes. It's 36. So if you don't change your inspiratory pressure, you're going to run into problems. But let's take a look at the PEEP. So at the PEEP, we're going to do an end expiratory pause. Okay, and let's take a look. Oh, sorry. So we're here at the end expiratory pause. My PEEP is 5. My esophageal pressure is 13.7. My end expiratory transpulmonary pressure is almost minus 9. What does that mean? What means is what's inside the alveoli, the PEEP, is much, much less than what's pushing outside on the alveoli by the pleural pressure. Okay, so what will happen at the end of exhalation? Every time the patient exhales, the alveoli will collapse. Then it starts to inflate during inhalation, and again, it will exhale. Once exhalation, it will collapse. So it will keep doing this opening and closing, causing atelectasis trauma. So what are we going to do about this to set a better PEEP? The idea here is to increase your PEEP to match the pleural pressure, so you have an end expiratory transpulmonary pressure above 0. So look here, when we increase the PEEP to 14, and now we can put a pause, you can, without a pause even, you can see that our transpulmonary pressure is 0. So the idea again to try to keep the end expiratory transpulmonary pressure at 0 or plus or minus 2. And look what happened when we increased the PEEP here. Look at the tidal volume. Now remember it was like tidal volume of 50 or something. Now the tidal volume is increasing because your alveoli inflate, and once it comes during exhalation, it does not deflate. Now, of course, when we did this, our end inspiratory transpulmonary pressure became 11. So it's not too bad. And of course, you have to make sure is the problem is the lung or the chest wall, because if the problem is the chest wall, you can actually have a plateau pressure of 40 or 50, and the transpulmonary pressures, which is what the lung is seeing, might still be normal. All that pressure, very high pressure, is just to inflate the chest wall. So this is like about the PEEP. There is so many ways of adjusting PEEP. Of course, like almost 20 or 30 ways, and in the literature, nobody knows how to adjust the PEEP. So of course, there is the PEEP FiO2 table, which I try never to use because it's so non-physiologic, and not everybody is recruitable, and everybody improves with PEEP. There is incremental PEEP. You can keep increasing the PEEP slowly, slowly, slowly. That's probably the easiest one. And every time you increase the PEEP by 1 to 2, you have to wait for a minute or two. Problem with this method, it actually has shown to be inferior to decremental PEEP. The other thing is, like, you might heard that, or probably heard that before, is PEEP does not recruit, meaning PEEP does not open the lung. PEEP is an expiratory phenomenon. So PEEP prevents de-recruitment of the lung. So to open the lung, you need to do recruitment maneuver, meaning, and recruitment is inspiratory phenomena, meaning you have to go on very high pressure, very high volume during inspiration, of course, briefly. Now the lung is open. Then you change your PEEP to prevent the recruitment. So let's talk about this a little bit. I will tell you my own preference is to do the pressure volume loop. And of course, it's not on every ventilator, but a lot of new ventilators have this tool. If you don't, you can actually do it manually. You put the patient on the volume controlled mode with the square constant flow, but you have to set very, very low flow, less than 5 or 4 liters per minute. So the inspiratory time becomes very, very, very long. But I'll show you why that PV tool is nice, because you can start your PEEP from whatever you want. I like to sometimes start from 0 PEEP and end at 0 PEEP. Again, this is transiently. I go up to pressure of 40, and usually you would hear that recruitment maneuvers, usually they call it 40 centimeter pressure for 40 seconds. There is, of course, a lot of debate on how to do recruitment maneuvers. And again, there's so many ways. But this is, I think, the one that's easy to understand. I will do the speed very low, and I want to put a pause at the end of inspiration. And I'll show you what happens. So let's start the maneuver. It told me that the maneuver, I was going to say no, the maneuver will take actually 45 seconds. So bear with me while the ventilator, as you can see here, it stops. It will start to go up on the pressure very, very slowly, and we'll start constructing the pressure volume curve. As you can see here, so the X is the airway pressure, the Y is the tidal volume, and you can see we start from peak of 0, going up, 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 nothing happening, no volume, until almost like about maybe 15 or something. Then all of a sudden, the air goes on, the volume goes in, and the lung starts to inflate. And by doing this maneuver, you can actually also calculate the compliance. Okay, so here it is. So this is the inspiratory portion of the pressure volume curve here. We're starting from zero, and as I mentioned to you, around, we're gonna move our cursor a little bit here. Around, you see, even the ventilator put an arrow for me. Around airway pressure of 15, the lung starts to open. So you can see that this area here is very poor compliance. So if you put your inspiratory pressure below 15 or your PEEP at 5, you're not doing anything. You're causing lung injury because the lung is very not, I should say, the respiratory system is very non-compliant. And then all of a sudden you have a straight, nice line here. And this is the area of the best compliance. So ideally, you want to keep your inspiratory pressure below this or your plateau pressure below this arrow here. And you want to keep your PEEP above this area here. So anyway, the inspiration happened, and we remember we put a pause, and that pause you see here, we put for 5 seconds. While there is no breath, what happens if you can see here, the volume still start to increase. So that's a recruitment. So that lung is recruitable, which is good news because recruitable lung you can improve with changing PEEP, with proning, with other stuff. Then you can notice the lungs during exhalation start to exhale, 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 and almost you can see like it's going down, and all of a sudden here, you can see that the lung is emptying, trying to collapse here. So where are we going to set our PEEP? And again, there's a lot of still debate of where is the best area to set PEEP here. So people would say this is the low inflection point, put it here. There is some more interest about doing the hysteresis. Um, so what is hysteresis? I have to do this. Hysteresis is the difference in the volume between the inspiration and exhalation. So it's all this area. So the ventilator here, actually what it did, it calculated the volume between here and here in all different points. So let's move our um, cursor here. And again, the idea is, I'm going down. The idea is to get, maybe set the PEEP at the highest point of the hysteresis here. So it's almost at, we're still at 15. So this is a very nice way of, setting the PEEP and see if the lung is recruitable or not. And it is by itself a recruitment maneuver too. Um, Again, there's a lot of debate on how to set it, but you can set it here. Still, the hysteresis is pretty hard, but then you would notice that again, there was no much volume here. So if it's up to me in this patient, I would set the PEEP at least at 15 or 16. So this is the whole respiratory system. The other, if you have an esophageal balloon like we have in our patients, instead of plotting airway pressure versus volume, we can actually uh, plot the esophageal pressure versus volume. And if you remember, that basically gives us a chest wall compliance. We're not really that interested in it. The chest wall compliance doesn't change much between inhalation and exhalation. We're interested about the lung compliance. So if you plot this, you're going to get the same curve, but instead of airway pressure, again, we're talking about transpulmonary pressure. So if you want to you want to make sure that you're setting uh, your end inspiratory transpulmonary pressure below 15 or below 12, and you can see the tidal volume here. And of course, at your end of exhalation with the PEEP too. So this is another really nice way to do this maneuver. Problem with this maneuver, of course, for a patient in respiratory failure to tolerate 40 seconds or 45 seconds, it's not going to happen. So if the patient is actively breathing, you are going to get all messed up. So most of the time, the patient has to be really paralyzed to do this. Versus if you have, again, esophageal balloon and stuff, you can adjust the PEEP without the patient being paralyzed. So with this, we talked about the little bit of the PEEP, little of the recruitment maneuvers, little of the benefits of esophageal balloon. Um, I want to go quickly about mechanical power. Um, and if you remember, so let's calculate the patient's mechanical power here. If you remember the formula, we are in pressure controlled mode. Um, if you remember the formula, and I will tell you for it again, it's in pressure control, it will be 0.098 multiplied by the minute ventilation, which is the respiratory rate and tidal volume, multiplied by the peak airway pressure. So let's go to our patient here and calculate it. So we have 30 multiplied by the minute ventilation is 4. Sorry, the math would take me a little bit. Oh, sorry, I need to write all of these things. I'm usually okay with math, but now I'm having a mental block. So let's go through it again. It will be 0.098 multiplied by the respiratory rate, multiplied by the tidal volume, multiplied by the driving pressure. Okay, so let's take a look at our patient. So respiratory rate, we have our patient is 20. We have tidal volume of 200, which will be 0.2, multiplied by driving pressure total is 20, sorry, it's 15 over 15 of PEEP, so total of 30. So it comes as 600 multiplied by 0.2. I need a calculator quickly. Sorry, bear with me. So that's what happens when clinicians are not good at math. Multiplied by 20, by 0.2, multiplied by 30. Okay, so in our patient here, we have mechanical power of 11.7. So I'm not going to torture you and switch him to volume control and you do this whole calculation, you get the idea. And I will put those slides of how to calculate them in the email that you will get with the link with that video. Let's, since we're talking about mechanical power, again, I want to show you the difference between pressure control and volume control. So we'll do the loops and pressure volume loop here. So if you remember from the PowerPoint slides, this is pressure control. And again, if you can remember it, this is the PEEP. Let me see if I can pause this. Okay. There, you can divide it into like almost half, like here. This is the resistive part, and this is on the left here will be the elastic part, and the elastic will be the PEEP part and the tidal volume, if you remember those things. But take a look at this graph and let's switch the patient to almost the same volume control, but almost same volume, almost same respiratory rate to see if you can see the difference between them. So we'll go, we said our tidal volume was 200. Our PEEP is the same, our respiratory rate the same. So let's take a look. Okay, great. Let's pause it. And again, you can see the difference. The pressure control was, the area is bigger, so the mechanical power is bigger. And we did some simulator studies that showed that the mechanical power on pressure control modes is higher than the volume control. Not all the pressure control modes, not the adaptive modes. We're talking about pressure control, continuous mandatory ventilation. Again, so here's in the volume control, if you remember, that right part here is the resistive part, and then the rest of the triangle is, this is the elastic dynamic part, and on the left side here, the PEEP part or the static elastic. part. All right, let's jump on a little bit on adaptive modes. And adaptive modes, of course, there is a lot to talk um, about. Um, uh, but let's see dynamic here, and let's get um, waveforms. Okay, so we'll switch this patient into ASV, which is one of the adaptive modes that I have available here on my ventilator. There is a couple of different adaptive modes, as you know, like almost 4 or 5 ones. Most of them are similar, but different names in different ventilator modes. Um, but again, I'm talking here about ASV because that's what I have um, on my simulator, and we're just going to increase. And let's make that patient kind of like normal lung mechanics, so you can see it. So what is ASV or AVM, whatever the names that you use is? The ventilator has the capability to measure our respiratory mechanics and try to find, according to different algorithms, it try to define a safe zone. What's a safe zone? It's like if you look here, this square here, it's called the safe zone. Why? Because, so I forgot to say that on the bottom here, the x-axis is the respiratory rate, and on the y-axis is the volume. According to equations in ASV is Otis and modified Mead equation, we find the least work of breathing or the breathing power is to either breathe very, very fast here on the right with very short, very shallow tidal volume, or breathe very slow with very high tidal volume. So the ventilator determines what's the best combination of the tidal volume and the respiratory rate. And you can see here it's called the target. So how are we going to set this? And there is a lot of studies around about the effectiveness of those modes, not only for safety during mechanical ventilation, but also for weaning. And recently, been a lot of interest in their effect on mechanical power. So what do we do? What do we set? So let's go to control. We said the most important thing is the percent minute ventilation. And how are we going to do this? Before we set um, any of the settings, we have to choose the patient. We have to make sure that we have the right gender and the right height. It happened to me before that I saw a small, short female, but getting very high tidal volume, and it's like, wow. Then when I looked, it was actually set as a male, was very, very tall. So the ventilator thought, oh, I need to give him high tidal volume. So we have here gender, either male or female, and we can adjust the height plus or minus. And according to this, the ventilator calculates the ideal body weight. So this is very important. Please don't forget it. Then we'll set um, the percent minute ventilation. And if you notice here, the dial goes from 25% to up to 350%. Hopefully, you'll never need this. But what is 100%? 100% meaning 100 milliliters per kilogram per minute for my ideal body weight. If my ideal body weight is 70, um, which is much less than my actual weight, but to have to set on my ideal body weight. So if you set me at 100%, it means that the ventilator will try to target to give me 7 liters per minute ventilation. And you can see here, minute ventilation 7.2. What will happen if you try to increase me to 150? Now the ventilator will start to target about 10.8 liters per minute. So according to this, of course, it will increase the respiratory rate and the tidal volume to get me into that safe zone. It doesn't want to go up so much high on the volume. It doesn't want to go up too much on the respiratory rate. It wants to keep me in the middle. So that's what you set. Of course, you have to set the PEEP And as we talked before, there's a million ways of setting the PEEP. So it's according to you, but the ventilator does not set the PEEP for you. In the new modes, which is not approved in the US yet, uh, called the IntelliVent, the ventilator will set the PEEP for you and the FiO2 for you. My problem is it will set the PEEP according to the PEEP FiO2 table, which I'm sure by time it will get smarter and find different ways, like we talked about, to set the PEEP. But for now, we manually set the PEEP, the FiO2. We still set the trigger, whether it's flow trigger or pressure trigger. Um, we have to set the rise or the ramp. You want to set a limit so the ventilator does not go above it. I just here increased the limit so high so the ventilator doesn't alarm. ETS, which is the expiratory sensitivity, only when the patient is spontaneously breathing because the breath will be pressure support. So I should have said from the beginning that if the patient is paralyzed and passive, ASV is a total pressure controlled mode, meaning the ventilator will give the same breath, same unless the mechanics changes. What happens if the patient is doing some of the work? Say the ventilator wants to give him 10.8 liters and he's doing and respiratory rate, for example, 19, and the patient is doing 10. So the 10 that the patient is doing the respiratory rate, this will be a pressure support breath, and the rest will be mandatory. So if you do that and you look at the taxonomy, this will be an intermittent mandatory ventilation mode, IMV. If the patient is breathing 20 above that limit, then all the breaths will be pressure support ventilation. So it's not only one mode, it's basically multiple modes. All right, so here the ventilator set our patient here at the rate of 19 and tidal volume of 588. The more the patient improves, of course, if the, for example, let's take a look at our, for example, we looked at our um, hmm, CO2, and you find that my end tidal CO2 is 31. So instead of doing a gas, for example, you did that gas and the PaCO2 is like 34, 35. Okay, I might be hyperventilating the patient a little bit. So let me go down on the percent minute ventilation. And of course, the more the patient compliance improved, and now because the more you're improving, of course, the tidal volume will go up. So you try to wean the percent minute ventilation. And once you actually go to 75%, it's almost a spontaneous breathing trial. So a lot of time, if you go down to 75% and say you don't need the 10 of PEEP, you're now on 5 of PEEP, and take a look what the ventilator was going to start giving, how much pressure. So right now we're people 5, and basically the ventilators, the peak is 13. So it's giving him only 7 or 8 of pressure. So it means that you right now the patient was in pressure support 7/5. So you can actually decrease it a little bit more. And once you're like, 7/5 or 5/5 and the patient's still doing good, that's you don't need to switch the patient to pressure support, especially if the patient is triggering all the breath. So if you find here the patient is breathing on his own like 15, 20, and the inspiratory pressure is so low, actually that's your spontaneous breathing trial. You don't have to switch to pressure support because most of the time, if the patient triggering all the breath, it will be spontaneous breathing trial. Again, of course, it's more complicated than this in adaptive modes, but this is just a quick about them. What I would do to last thing we'll talk about, I know because we're almost 1 hour, I want to talk about some of the asynchronies. So I will shut this and I will go back to my, sorry, let's go back to my, okay, um, this other simulator here. So how I just wanted to show you first the work shifting. So again, this is our patient with a tidal volume 515. So let's make that patient total passive, zero effort. And I want you to notice what happened to the airway pressure. Let's just stop this pause so it becomes obvious more. And you will see nice straight triangle up here. And, we didn't talk about this in setting the PEEP. It's called the stress index. It's one of the ways of setting the PEEP, but again, the patient has to be passive. But anyway, you can see that this is a very straight line because the patient has zero effort. So let's make our patient um, start to breathe like a little bit above the ventilator here. And let's make his effort really high. And again, notice what will happen to the airway pressure. Okay, I guess we can all see this big dip here. And the problem is you will see it a lot, especially in volume control. It gets missed because the ventilator does not beat. Matter of fact, your peak inspiratory pressure is actually much lower than before. And we're all happy. And if we do a plateau, and it's like, wow, our plateau is very good. We're protecting that patient. But look at that patient. This is the definition of work shifting. The airway pressure should never be like this. The patient is, and if you have an esophageal balloon, which we don't in that simulator, you'll find that the transpulmonary pressure is very, very high. So this could be very injurious. Again, so please take a look, be careful with this. So let's change on pressure control. Pressure control, even if the patient is doing the same work, so let's make him passive again, just so you can appreciate the difference. So right now, again, the patient is passive. The airway pressure is nice and straight. The flow is very nice and decelerating. Um, I think you can see that. And again, let's put the PMOS, meaning the muscle pressure, very high. So look what will happen. Of course, now we're adding PMOS, so the tidal volume will go very high. Look at the pressure. The pressure supported to the patient does not decrease. You can see a little bit convexity. It's kind of solid. But look what happened to the air, to the flow. After it was nice, decelerating, you can see the convexity. Um, it's doing this. So you can tell that this is also work shifting. Okay. And since we're talking about this, I want you to notice. Sorry again, I cannot freeze this, but you can see here. So this is the patient effort. You can see the convexity here. So if you have an esophageal balloon, you will find that the esophageal pressure is dipping because the patient is breathing, where I'm doing the arrow here, and then the patient relaxes here. But what happens? The ventilator is still giving the pressure here. So that's what we actually call delayed cycling. The patient's brain told him to breathe and stop breathing here, but the ventilator kept giving the breath. So this here there is delayed cycling because the ventilator again giving extra time. Okay, so let's see what happens when we lower the inspiratory time, because here our inspiratory time is 1.74. So I will actually try to reduce it, and let's see if we can match that patient. Okay, so here actually I shortened the inspiratory time probably too much. So you can see like it's still convex here, meaning the patient is still breathing, but the ventilator decided, nope, my zero 0.6 seconds or 0.7 seconds is done, so I switch to exhalation. So this is early exhalation. Sorry, early cycle. So what we're gonna do, we need to try to match this to the patient. I know it's kind of really tough to do that without an esophageal balloon or EDI. Also, the problem is you might spend some time and you think you got it perfect. Of course, 5 minutes later, the patient is different. Now he's sleeping. Now he's in distress. But if you look here, now we matched exactly the convexity here start to happen, almost stops at the same exact time that a ventilator cycles from inhalation to exhalation. So this you actually got it pretty good here. So we talked about work shifting, early cycle, delay cycle. I want to show you missed effort and delayed trigger. Again, most of the time it happens in COPD people who are having, of course, high resistance and high compliance. So I'm gonna exaggerate a little bit here and on the rate and everything. Um, create basically what I'm gonna try to do is create auto peep so you can see um, difference. All right, so let's see here. I guess you can see here. Remember, if we talked about that's delay trigger. So you can see the flow started to change here, but it takes the ventilator almost zero point 0.4 seconds to trigger the breath. Just delay trigger. As we said, most modern ventilators take only 0.03, 0.04 seconds. So imagine you're the patient, you're trying to breathe, but the ventilator is like, nope, 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 and gives you the breath. So very, very uncomfortable, cause a lot of agitation and stuff like that. So what I'm gonna do is, again, I want to create very high tidal volume so I can show you the mist trigger and the auto peak. So let's make even the eye time longer to create auto peak. Let's make it 1 to 1. Okay, here you go. So now this patient, if you look at the here exhalation, and you can see here, that's a patient effort. This is delayed one, and you will see it later, another one that is totally missed effort, especially if his effort is not that much. Um, okay, sorry. Again, delayed effort. I will make the rate higher, so I hope you can see it. Of course, you can see the auto peep. Every time here you go. Sorry, every time it does it, the screen changes, and I do not think I can control the time. So maybe we'll just reduce the respiratory rate a little bit, and the patient effort. So I just want to show the mist trigger or and of course, because I'm trying to do this, here we go, this part. Again, I don't know why the ventilator cut the rest of the breath. Let's just give it 1 second here because you will see a bump here during the flow, but there's no trigger after it. Hmm. I'm trying to increase, sorry, again, the synchronies or asynchronous online simulator is really sometimes hard to match it. But if you look at your patient with COPD or very high compliance with auto PEEP, here we go. So this usually the patient wanted to breathe here. You can see this hump here. That's beautiful. So usually that's patient effort. So the ventilator should have given him the breath here. So this is a missed trigger or ineffective um, trigger. I think we've now been an hour and 5 minutes, so I will stop sharing, and maybe if you have um, any questions or um, if you want to chat about something or have any comments, we'll just give 5 minutes. Uh, while we're waiting, again, thank you for attending this. And again, this is being recorded, and I will send them to your emails, and maybe later on I will put them into in our YouTube channel. But you should be getting this video